All right, today we are learning about something called logarithms. And to kind of build up to our understanding what they are, we should kind of first answer these questions. So finding the value of x for each of the problems below. Then the hint here is answer the question, what power? So this first one, 3 to the x power equals 9. And we should know that x equals 2 here. And we know that because if we did 3 to the second power, we would get 3 times 3, and that would equal 9. We can similarly find 2 to the x power equals 8. So what power does 2 need to be raised to equal 8? We would know that, hey, if I take 2 times 2 times 2, that gives me 8, and I use 1, 2, 3 2's in a row to multiply to that, so x equals 3 there. Now, if I repeated this for 2 to what power equals 32, okay, then I'm looking at 2 times 2 gets me to 4, times 2 gets me to 8, times 2 gets me to 16, but we need to go one more time to 32. And we use 1, 2, 3, 4, 5 2's, so my x is equal to 5 in that case. That's what we're talking about when we're talking about taking logarithms, all right? And let's try this on a couple example problems as well. Maybe if you're watching the video, firm up your understanding on at least problem 1 and maybe problem 5 here. If we do this, okay, what power does 4 need to be raised to equal 64? All right, we can try 4 times 4, but that equals 16, so that's not far enough. If we do that again, another 4, okay, that will get us to 64. So in the case of problem 1, x equals 3. If we try that for problem number 5, 5 to the k power equals 625, trying to figure out what k equals. Okay, 5 times 5 is 25. That doesn't go far enough. Times another 5 is 125. That doesn't go far enough. So if we go one more time, that will get us to 625. So my k value here is equal to the number 4. So let's take this concept and formalize it into notes, and specifically in the context of this new term, logarithm. So jot this down on the top of our note sheets. Logarithm, the exponent or power to which a base must be raised to yield a given number. We're going to see these things in kind of two different forms. First thing is exponential form. This is what we're used to. We take some base number b, we raise it to an exponent, and we get an answer. And if you want to throw some labels in your notes here, I would label b as base. Notice how this shows up in both. And I would label the x as our exponent. And notice how in logarithmic form, we're gonna basically repeat that relationship just in a different order. Notice how my base number b is at the bottom of my logarithm here. We're taking the log base, and we're taking the logarithm of n. That was our answer in our exponential form. Now it is what is part of our original problem in our logarithm. And my exponent in exponential form is going to become the answer in our logarithm. So let's kind of practice rewriting just so we get a good idea of the structure here. In example problem 1, 2, 3, 4, we're going to kind of bounce back and forth for each of these. So my exponential form, base 5, exponent 3 equals 125. We're not solving anything. We're not evaluating anything. All we're doing is rewriting that relationship in logarithmic form. So we have a log base 5. Notice how my 5 is a smaller number. It's like an exponent, but reverse. We are taking the logarithm of 125, and that will equal 3 as our exponent. Okay, all we did was rewrite those three numbers in a different order. Same can be done with variables. Okay, in example 2, we have a log. We're going to take a log. The base is going to be m there because that's our base number. We're taking the log of p, and that exponent there is n. We're raising it to the n power. We can also work the other way, going from logarithmic to exponential. Okay, my base is 2. That's the low thing in my logarithm. So my base is 2, my exponent is 3, and my answer or argument is 8. And the last one, my base is x, my exponent is y, and my answer is z there. Now, let's combine that idea with what we did in our kind of opening exercise talking about what power we're looking for. So if we look at examples 5, 6, and 7, we're given logarithms and we are going to evaluate each logarithm. So we're going to figure out, hey, what is log base 3 of 9 equal to? So what I'm going to do is I'm going to first rewrite it and say, hey, all right, log base 3 of 9 is equal to x. Let's throw some variable in there, some unknown. From there, we can rewrite it as a exponential form. 3 to the x power equals 9. And then just like we knew before, hey, 3 times 3, or 3 squared, is what's going to get me to 9. So we know that x is equal to 2 there. Right? If we did 3 to the second power equals 9. Similarly, we can do that with log base 4 of 64. So I like to write that variable at the end to kind of say, hey, we're solving for some unknown. Log base 4 of 64 equals x. And then I'm going to write base 4 to the x power equals 64. And I should be able to determine from that x equals 3, because I would need to do 4 to the third power equals 64. But again, my answer is 3 there if I was trying to evaluate that logarithm. And finally, the log base 2 of 64, you can even say, hey, if we're not using our x this time, maybe we just say, all right, we're trying to figure out what's going on, use a question mark. We have a base 2. We are raising it to some power. That is equal to 64. And we would need to raise it 2 to the fourth power to get 64. So my answer there is 4. And in all these cases, our answer, we're evaluating the log. So I'm going to write one more step below. Log base 3 of 9 equals 2. The log base 4 of 64 equals 3. And this last one in orange, the log base 2 of 64 equals 4. And I'm realizing right now that I made a mistake. Hopefully some of you guys caught it. It is not 2 to the fourth power. That is incorrect. So my work there for my orange example is wrong, which is why it's important to kind of go slow and check your work. Let me kind of erase that and back up. Set it up right. Still going 2 to the what power equals 64. But let's think about this. If we go 2 times 2, that gets us to 4, times another 2 gets us to 8, times another 2 gets us to 16, times another 2 gets us to 32, and finally, that last one gets us to 64. So it would be 2 to the 1, 2, 3, 4, 5, 6. 6 power equals 64, meaning that the log base 2 of 64 equals 6. Now, there's a special type of logarithm called the common logarithm, and that's anything with a base of 10. One thing to look out for is we might write this logarithm without any base noted. Look at that green example there. Log of nothing, or log base nothing of 1,000 is the same thing as saying log base 10 of 1,000. And in both cases, these are equal to 3. What's cool about these is we can use the log button on our calculator. It can be used to calculate base 10, but can't be used to calculate the base of anything, or the base of anything else. So only can be used for base 10 for that common logarithm. In examples 8 through 10, let's just do some quick evaluations using our calculator. So I'm going to make sure I really highlight this. Use your calculator. And all we got to do for example 8 is punch in log. It'll give us parentheses, and then we just type in 10,000. And we're going to see that we get, if we punch that in there, we should get an answer of 4. Let me do it on mine. Log 10,000. Yep, we get 4 as an answer. So again, using our calculator for log 9, and we're going to round this to 2 decimal spots. We just punch in log 9. In this case, we get 0.95. And the last one, log of 237. We're going to round to 2 decimal spots. Again, we get 2.37 as our answer. There's one more kind of quick skill we're going to learn with logarithms today called changing the base. This is a unique property where if I have a logarithm with some base a, I can rewrite it as a division problem, taking the log of x divided by the log of a, and I can rewrite it with any base I want. What's powerful about that is, let's say we had the log base 2 of 8. Okay, what we can do is, instead of thinking through that mentally, we can rewrite it as the log base 10 of 8 divided by the log base 10 of 2, and then we can use our calculator to evaluate it as opposed to evaluating with mental math. So this will be really helpful for logarithms that are not as simple to evaluate and have different bases other than base 10. Let's see how this plays out, right? If I have the log base 2 of 5, I can take 2 to the first power, and that equals 2. I can take 2 to the second power, that equals 4. And I can take 2 to the third power, and that equals 8. But we're targeting 5 there. So there's not a clean number. We're going to have some weird decimal answer there. So what we can do is we can rewrite this log base 2 of 5 as, we can rewrite it as a change of base formula. We can take log base 10 of 5 divided by log base 10 of 2. Okay, notice that's the common logarithm, and we can use our calculator. And we can simply just go log of 5 divided by log of 2. And remember that fraction is our division. So our answer there is 2.32. Now this is something we would have never gotten by mentally working through it. Using that calculator, using that change of base is really helpful. Same thing can be done with example 12. And at this point, pause your screen, unpause it, try it for yourself as you go. We can take the log of 50 divided by the log of 2. If we do that, log of 50 divided by log of 2, rounding to 2 decimal spots, we get 5.64. And let's just try this on 2 more examples, then we're done for the day. We have log base 3 of 20. So I'm going to rewrite this with my change of base. I have log of 20 divided by log of 3. So log of 20 divided by log of 3. That equals 2.73. And lastly, log of 4.4, log base 4 of 4.4. If we rewrite that as our change of base, log of 4.4 on top, log of 4 on the bottom, and we'll get 1.07 as our answer here. So a lot of different skills working with logarithms. These are kind of the base skills that we'll work through the next week. And hit some practice problems today. Check out Canvas to see what the instructions are.